Welcome back. This is lecture 19. So let's continue our discussion on noise as we were doing in the last few lectures. And again, we'll start off with the same example of a common source kind of configuration, and then see what are the other issues with that configuration if we use it as is, right? So, but before going there, let's continue our discussion of how to what are the other ways of what are the other ways in which your circuit can get affected by thermal noise, right? Till now, for a transistor, we have only taken into account the noise due to the fluctuations in the drain to source current, right? As it turns out, that is not the only cause of thermal noise in a MOSFET. We are going to talk about a couple of them in today's lecture also. Okay, so let's start off with that. So now when we draw a symbol of MOSFET like this, what are you essentially saying? How does the layout of this symbol look? So if I take a cross section, if I slice the MOSFET in a wafer and look at its cross section, this is what we are going to see, and we have seen this multiple times in this course already. So essentially, this is a repetition of what we know. And this is n plus, this is n plus, and if I try to draw a three-dimensional kind of figure, this is what it should look like. This is a gate oxide, and this is probably the n plus, right? The reason I am drawing this out here is essentially because this what we have here is a gate, right? This is a polysilicon gate. Typically, this is a polysilicon gate. It can also be a metal. It depends from technology to technology, but typically this is a polysilicon gate. Now when you look at the entire stack of a CMOS process, a bulk CMOS process, then ultimately we know that we'll have to connect everything via some metal line, right? And that connects multiple transistors and multiple passives together. Ultimately, we have to make a circuit, which means we have to establish metallic connections between nodes of different parts of the nodes of the network. So how do you do a metallic connection? Because from our very preliminary knowledge on wafers, what we understand is that when you actually make a transistor, you do it layer by layer, right? You do not make one transistor at a time and then go to the next transistor and go to the next transistor. We do not do that. So if you have a million transistors, right? So we first probably will perform the operations on etching your wells wherever necessary. Then we will be performing operations of doping for all the transistors wherever necessary, and so on. Similarly, when you want to connect multiple nodes of the transistors or passives, so we'll be digging holes and we'll be depositing metals in such a way that all the transistors in the network are connected as we essentially want. So what does it essentially, what is the implication of that for circuit designers? The implication for that is, if you look at the metal stack, if you look at the stack of, if you look at the cross section of the entire stack, this is what you are going to observe. So if I just look at the stack, so that, when I'm doing this drawing, I am not essentially taking into account that there is anything that is connected. I am just looking at the stack from a sideways direction. Okay, so let's say this is your p-type wafer, right? So you will have a p-type thickness, right? So let's say this is p-type thickness. Then if you want to connect anything if you want to connect any metal layer, right, any metal to the substrate, what you have to do, you essentially have to dig a hole, deposit the appropriate dopant, right, and then establish a connection between this p-type layer and the next layer that you are planning to connect to. Now, what is the next layer? The next layer is essentially you will end up having oxides, and on top of that you are going to have, let's say, a metal layer. Now this is not drawn to scale. You are going to have metal layer. Let's say I call this metal 1. Okay, and if you want to connect this metal layer to the poly to this poly, so there will be holes in that layer, right? So as you can see, I have not drawn the oxide to be in a continuous fashion. So there are holes in that layer, and you are going to and this metal, when you deposit, these metals are going to seep in. Okay, these metals are going to seep in and make the connection. Right. Similarly, obviously, you need to make it P plus also. So I'm not going to that amount of detail. And let's say if you have only one metal layer, then probably you will be limited by connecting. There are only so many ways you can connect multiple nodes if you have only one metal layer to use, because ultimately otherwise you'll have to go all around the chip to connect one node to another, right? And you cannot ever afford a crisscross between two nodes, otherwise they will get physically connected. Okay, so in order to avoid crisscrossing between nodes, or rather in order to avoid physical overlap while connecting between nodes, right, and while ensuring that you do not have to go all around the town to connect point A to B, what you need is essentially more metal layers. Okay, so processors usually provide more metal layers, and let's say I call this another metal. So let's say I have another layer of oxide, and on top of that I want to connect, I deposit another set of metal layer, and I call this M2. And if there is a gap in the oxide, this M2 is going to connect to M1 through this gap, right? Okay, so let me call this M2. Okay, by the way, these gaps are called VRs. It's called VR1 because it is connecting, rather generally this is called VR1. The one that connects between M2 to M1 is called VR1. That's a typical nomenclature, but we don't have to pay too much attention to that in this course. And now, as you can readily guess, if I want more flyovers, right, in my city, if I want to go from point A to point B and want to have multiple crossovers, then obviously I want multiple flyovers, which means that, which in this parlance translates to, we will want to have multiple metal layers which run on top of each other, right? So as it turns out, there are several processes which gives you metal layers. The 4 metal layer processes. There are some metal processes which give you as high as 8, 9, 10 metal layers, right? And needless to say, if your process has more metal layers, it will be more expensive. Just like it takes significant amount of money to build flyovers. Similarly, building flyovers on the chip will also cost you more. Okay, but I mean, fortunately, I mean most RF design processes give you a fair amount of metal layers, so that it helps you make the connections, right? So a choice of a technology, that's why with respect to the available metal layers is also sometimes becomes important, right? So now why am I telling you all these stories? I'm telling you all this story because now note that just because now let's focus our attention to the cross section of the transistor. Now just because I want to connect one gate, right? So let's say I have this gate, and that gate has to go all the way out of the chip and connect to the antenna, right? So essentially I have this, and let's say this is a physical resistor. I don't know, let's say it's a physical resistor, some RS, and it has to connect to the gate. Now how do I make that connection? I'll have to note that the gate is somewhere connected. Note that the gate is on M1, right? And if I have to connect something to the gate which is at other end of the which is not sitting next to the transistor, then obviously I'll have to make a physical connection between this gate to that. And note that now, because I have to cross over multiple flyovers, right? So I have to develop a contact or a via that connects my M1 to probably an M2, correct? So and the part that I have also missed mentioning, if most processes, the gate is a polysilicon layer, which is also different from metal layers, which means that you might want to you will probably have a separate polysilicon layer which needs to be connected. If you want this to connect to metal 1, you'll have to dig holes from metal 1 onto polysilicon. Okay, now the question is, where do you dig holes? Because your gate has certain amount of area, right? Your gate has a length and your gate has a width. So where do you dig the holes? So do you drop your contact here? Do you drop your contact from the top metal, from metal 1 here, or you drop your contact here? So as it turns out, because of process reasons and because of reliability reasons, it is not recommended that we drop the contact directly in the middle of this slab of polysilicon, mostly for reliability concerns. So in most cases, your foundry will not even allow you to connect any via at the middle of your transistor. Moment you do that, it will say an error. Okay, so in most cases, the connections will be done at the edges of wherever the gate connection ends. So essentially, you are going to end up having to connect your polysilicon vias somewhere over here. So you are going to have some via here, some via here, and this will go up. This is going to go up and connect to maybe an M1. And so on. Okay, and this M1 will probably it will route to somewhere else and then maybe connect to a resistor somewhere, right? Okay, so the key thing to note here is that you are unable to establish a connection all across the gate with respect to the previous with respect to let me rephrase, you are unable to make a connection all over uniformly all over the polysilicon gate, right? So what does it mean? This essentially means that how does the current flow? The AC current, which essentially comes through M1, establishes its contact at the edge, right? And now note that we are not talking about DC here, because DC there is anyway no current, because we have it's a capacitor. Since we are bothering about AC, so we understand the fact that there is a distributed capacitance all across the channel between the polysilicon gate and the channel, right? And there is a distributed resistance. There is a distributed resistance in the channel, right? And there will be, it's like almost like a transmission line of resistance and capacitances, right? So now when you have these type of scenario, what do you end up happening? So I can model this as almost like a lumped element at a very crude model of this entire situation is, so my gate, I can essentially model this as some resistor Rg in series with the gate, right? And your MOSFET comes along with this resistor. So this resistor Rg is the gate resistance due to polysilicon grouting. Now note that this gate resistance is of no consequence if you are doing AC response at very low frequencies where the capacitance is CGS capacitance is almost open circuit. But if it's not, then probably you are going to get an effect of Rg. Now there is a way to reduce this effect of Rg, and that is as follows. So again, if I draw the cross section of the MOSFET, so I'm not drawing the drain and the source, but we understand that this is L and this is W, right? So why are we having so in such large why are we having this problem with Rg? Is because the foundry is telling you that you can only put your contacts here at the edge of W, not even at the edge of L, at the edge of W, right? So if you have long W, right, so then you are going to have large Rg, right? But there is a way of fixing this, and the way of fixing this is to say that I am not going to use a long W, I am going to use multiple small W's and put them in parallel, right? So essentially what we are saying is, if I have one single transistor of W by L, if it has an Rg resistance associated with it at the gate, if I break this transistor into, let's say, two transistors in parallel, right? So if I say two transistors in parallel of value W over 2 by L, right? What will happen to this Rg? This Rg will also become Rg by 2. This Rg will also become Rg by 2. But note that these transistors are now in parallel, right? So if I connect them node to node, right, then I can effectively say that the Rg has gone down by a factor of 4. isn't it? Uh, so why factor of 4? Because moment you reduce one W by factor of 2, Rg goes up to factor of 2, and you have two transistors in parallel, so our Rg goes down by factor of 4. So by doing this, you will be able to reduce the value of Rg. Okay. So now the top level view of this transistor, right? So now if I sketch the top level view, right, looking from the top, it should look like this. So this is your gate. Let's say this is your drain. This is your source, and you have a gate connection somewhere over here, right? So maybe you have multiple contacts. By the way, you cannot make a one large contact. The foundry is going to limit you and say that this is the maximum size of the contact that you can use, which means you have to use multiple of them in parallel. So let's say I'm showing two of these contacts here in parallel, right? So what is W, what is L here? So clearly this is L, right? This is the length, the area is traveling under the gate, and this is W. If we split the transistors into two different transistors having half the W, what are we doing? We are essentially saying that we are going to use, but the same L. So let's say I call this D1, right? I call this S1. I call this also S2, and I call this D2. Correct? So then I can basically say that since S1 and S2 are anyway connected, so I can remove this extra stuff and make it a single contact. I call this S1, basically the same source, and D1 and D2 I am going to physically connect with metals. But the key thing to note here is that the L remains the same, right? And these two transistors are in parallel, but the W has gone down by a factor of 2. These are W by 2, right? So since these are W by 2, you essentially end up having smaller resistances, right? So these will be obviously be also physically connected. Okay, so this becomes your gate. Fine. So that is one way of reducing the gate resistance. Now your question might be, why am I so bothered about reducing the gate resistance? The reason we should be bothered about reducing the gate resistance, other than the fact that it can affect your AC response, is the effect of noise. Because this is a physical resistor, this is not a model resistor, this is a physical resistor, so which means that it is also going to contribute to thermal noise. Okay, so which means that my noise model now has of the transistor has an extra Rg, where this Rg is also contributing to thermal noise, and we have this In anyhow. Correct? And the pass spectral density of Vn of this will be, this will have a PSD of 4 kT, voltage noise pass spectral density of 4 kT Rg. Okay, but you see that there is a geometry way you can lay out the transistor in certain way to reduce Rg. So that is something that you can do. There is another aspect of thermal noise in transistors, which is intuitive to understand but difficult to analyze. So I'll give you the intuition and I'll give you the result without doing too much of analysis. but hopefully I'll be able to convince you why the result is like that. So another contributor to thermal noise in MOSFET is this. So now note that what is the source, what is the reason I have thermal noise in the channel is because ultimately we have some channel here, right? And there are fluctuations in the channel that is causing the change in current between the drain and the source, and that change in current is leading to thermal noise, right? So there is a noise current, right? That is flowing. Now note that at high frequencies, right, where the gate to source capacitances cannot be neglected, or other way of saying that the distributed capacitance in the channel cannot be neglected, a part of this IN will flow into the gate. It has to flow, right? Because at high frequencies it can see a fairly low impedance gate, because the effect of the capacitance will reduce at high frequencies, which means that there can be an IGN. There can be a noise current due to the channel charge fluctuation. Now note that this is nothing to do with the physical RG. It is separate from RG. Even if you have made RG to be zero magically using some magical process, this IGN will still be there. You cannot do anything about it. Moreover, the second point is this IGN is you will not experience this IGN at around DC, right? Simply because the capacitor will block all DC currents, you are not going to see the effect of IGN. Okay, but naturally, if you go to higher and higher frequencies, you are going to see this IGN come out. Okay, so as it turns out, after doing a lot of device physics and a lot of maths, people have figured out a empirical formula to estimate the power spectral density of IGN, and that is as follows. Yes, IGN is approximately equal to 4 kT GIGN, where GIGN is approximately equal to Gm over 5 times omega by omega t whole squared. Okay, where now if I stare at these terms, it should not be a surprise to understand that, to appreciate that this IGN current power spectral density is proportional to Gm, because the root cause is IN, right? And the power spectral density of IN is proportional to Gm, so it is expected that the power spectral density of IGN will also be proportional to Gm. And also we see that at around very low frequency at DC, the power spectral density of IGN essentially goes to 0, but at higher and higher frequencies, right, it kind of has a high pass shape, right? At omega, the value of omega, as omega increases, your power spectral density increases, and omega t is essentially Gm over CGS, right? So that is the transit frequency of the device. By the way, this expression is valid only when omega is less than omega t, right? Your IN never goes to infinity, right? So it is not expected that your SIGN will also go to infinity. So this is valid when omega is less than omega t, right? Okay, or rather I should, if I have to be strictly accurate, I have to say much lesser than omega t, but I'll keep it at omega less than omega t for the time being. Okay, so note that this IGN you cannot do anything about. It will be there. But the good thing is that if you are biasing your transistor in such a way that omega is much lesser than omega t, or rather omega t is much higher than the frequency of your interest, then the effect of this IGN will again be negligible. It can be made negligible by biasing your transistor for very high omega t or very high ft. As you see that this omega t or ft keeps on coming back, right? We discussed this in some detail quite a few lectures back with respect to increasing the frequency of operation of our network, of the transistor, right? it seems like it is also having a significant it can have a significant impact on the noise also, right? So that is why in most RF circuits you will see that there is a lot of effort in biasing the transistor in such a way that you maximize FT. Okay. The another key aspect to this of this noise, this IGN, is IGN and IN are obviously correlated, right? Source is the same, right? But as it turns out, again, I'm not going to show this. If you do the math, you you do not take into account correlation, you assume they are uncorrelated and do your all your analysis, right? So you do not end up with too much of a deviation from uh, what you would get if you consider correlation, but the math becomes significantly simple. So what we'll do is in this course we'll avoid, even though we understand there is a correlation, we are going to avoid the effect of correlation going forward between IGN and IN whenever we have to deal with IGN, right? So this is just a disclaimer that I am giving you right now. In the rest of this lecture and probably in the next lecture also, and in most of this course will not talk about IGN, but for a case of an LNA design where we'll have to be where we would like to go for extremely low noise design, you will see that in most of the course we will not be talking about IGN, right? But if somebody talks about IGN, you should know what one is talking about. Okay. So in the rest of today's lecture, let's take an example again for a common source amplifier. Put the effect of RG into account and then find out the noise figure at the output, right? So in the previous lecture we saw that what happens if we input referred everything and found out the noise figure. That has some value, but as you saw that we have to deal with correlation, this, that. But when you are doing, if nothing is specified, you can take the noise figure anywhere. So we'll take an example of calculating the noise figure at the output, and you will see that it's fairly simple to calculate the noise figure at the output, right? In most cases. Okay. So let's take that example. So let's say again I have our good old common source amplifier. This is a source resistance. This is Vn. I am calling this common source amplifier, but for the time being, I am assuming that the load resistance at the drain is noiseless, and I'm only interested in the output current. One of the primary reasons is, as you must remember, so we had made our changes in such a way that instead of using a load resistance, we used an inductor to get rid of the headroom problem. And the good thing about the inductor is that an ideal inductor does not have any R, which means it does not contribute to noise, right? So I do not have, if it doesn't contribute to noise and gives higher impedance, I do not have to bother about it. I'll just let it be, and now let me, for the purpose of this lecture, I'll be interested in only the short circuit output current. Okay, fine. So what else do I know? I know this inevitable CGS always comes into picture, and I also know that now I have to deal with now I have to deal with this RS also, right? Sorry, this RG also. And for the time being, we are not considering the IGN noise, that is the correlated noise that is coming from the from the channel to the gate, right? For the purpose of this calculation, we'll keep it simple, and let's see what happens. Okay, fine. So again, if we recall, what is noise figure or noise factor? Noise factor is total noise at output by noise due to source only, right? When I say source, I mean source resistor. So what is the total noise at the output? So SVN out. So what are the noise contributors? Clearly you have the IN, right? So let me just write out the noise in terms of transfer functions. Then I'm going to put as Vn. So your ISC, I should say ISC noise, not the voltage, not the signal. So ISC noise is IN plus what? When I'm doing noise analysis, I do not need the source. I can get rid of the source. But I know that RS and RG play I can model them as voltage sources in series, and since they are in series, the equivalent voltage source using our Nyquist noise theorem essentially 4kT. I can club them into an equivalent resistor of RS plus RG, and I'll get some equivalent noise voltage, right? So that's what we're going to do. So I am going to say this is Vn in, right? So we are going to get noise due to Vn in, right? So now what will be the noise due to Vn in? So this is Vn in times what? The gate to, I have to find out the gate to source voltage and multiply it with Gm to get ISC, right? So if I am doing in frequency domain, the gate to source voltage is simple. This is basically low pass filter, right? So 1 by 1 plus Rs plus Rg times j omega cgs, right, times Gm is essentially the transfer function from or rather is essentially this total thing is essentially the total short circuit noise current, right, in using all phases and everything into account. But if I have to take into account the power spectral density, so as VCN, this will become 4kT gamma Gm due to IN plus Vn in is 4kT Rs plus Rg, right, and times the transfer function mod of transfer function squared, which is Gm squared by 1 plus Rs plus Rg times omega square Cgs squared, right? Okay, fine. So this is the total noise at the output. And what is the noise due to source? Source is essentially 4kT Rs times that transfer function squared, right? So what I'll do, I'll just, instead of keeping on writing this transfer functions, this entire thing every time, so this I will call at mod of H squared. Okay, so noise due to source is 4kT Rs mod of H squared. So then what is noise factor? Our noise factor is 4kT gamma Gm plus 4kT Rg times mod of H squared plus 4kT Rs times mod of H squared by 4kT Rs times mod of H squared. So this is nothing but this and this are same, so this is 1 plus all the 4kTs cancel off, so we get 1 plus Rg by Rs plus gamma Gm by Rs mod of H squared, right? So this is your noise factor. So what is the goal? The goal is to ensure that the noise factor is as close to 1 as possible. So what do you need to do to ensure that? So at very low frequencies, right? What is very low frequency? Very low frequency means I can neglect this term. I can neglect this term with respect to 1, right? Very low frequency means the capacitor is not in picture. So which means that at omega much less than 1 by the corner frequency, that is Rs plus Rg times Cgs, right? So what can I say? Your mod of H is essentially 1, then your mod of H is approximately 1. So your noise factor is 1 plus Rg by Rs plus gamma Gm. I made a mistake here somewhere. I should have written this as Gm squared H squared, right? So I should write this as, instead of making this, I should have, so this should be H squared. So I should have written these as times Gm squared times Gm squared times Gm squared, right? So mod of H squared Gm squared. So this becomes, okay, so this becomes, the Gm comes in the denominator, right? Yeah, Gm comes in the denominator. So that is unit wise also this makes sense. So this becomes gamma times, or gamma by Gm Rs. Okay. So as a designer, what, to reduce F, right? To reduce F, what are the things that we are going to do? We are to reduce F, reduce Rg. This we can do by layout and increase Gm, right? So again, so basically increase Gm means you end up burning more power, right? So as you see that almost there is no way of getting rid of the problem of burning more power. But this we did for low frequencies, right? At where we can neglect the parasitic capacitance of the CGS. But what if we cannot neglect, right? So what if we are operating at frequencies where we cannot neglect? Then what is the better approximation? Mod of H squared is 1 by 1 plus Rg plus Rs whole squared omega square Cgs squared, and this is Gm squared times, right? So this is Gm squared times. Okay. So if we say that if omega is greater than 1 by Rg plus Rs times Cgs, then Gm squared H squared is equal to essentially Gm by Rg plus Rs times omega Cgs whole squared, right? So this is essentially equal to Gm by Cgs is omega t. So this becomes omega t by omega whole squared times 1 by Rg plus Rs whole squared, which essentially means that what does the expression of F boil down to? So F becomes 1 plus Rg plus by Rs plus the additional term which is this term, right? Gamma by Rs h mod of h square times Gm, which is gamma by Rs mod of h squared. So mod of h squared is essentially omega t by omega whole square times 1 by Rg plus Rs whole square times 1 over Gm squared times Gm. Correct? Okay. Which means your F boils down to 1 plus Rg by Rs plus if I assume now that Rs is much greater than Rg, then this becomes, this one of these Gm goes, this becomes gamma Gm Rs times omega by omega t whole square. Right? So which is approximately equal to, this is obviously assuming Rg is much less than Rs. I can then effectively neglect Rg from the second term also. So your F becomes 1 plus omega by omega t whole square times gamma times GMRS. Now this is again critical because as you can see that your noise factor again is, it seems to have a high pass shape, as in if you keep on increasing frequency your noise factor is increasing. So when you are trying to design a low noise amplifier and you want to keep the noise factor down, then you have to ensure that you design for maximum FT always, right? So key takeaway is, for low noise design for max omega t. Okay. Now note that in this case you in this case what are the free variables? Obviously your RS you cannot change because RS normally comes with source. But what about GM? I mean, one might say that I would like to take omega t out and write it in terms of GM. Sure, you can. I mean, break your GM into break the omega t into form of GM. But again, I mean, you are essentially, as you see that you have omega t squared in the denominator and GM in the numerator, you are essentially going to get the kind of the similar trade-off. That is, in order to reduce noise factor, you'll have to increase your omega t. The other way of thinking about it is that, let's say you have fixed your GM for some other reasons, right? What are those other reasons will become clear in the later lectures. But if a GM is fixed, then ensure that you bias your transistor for maximum omega t, right? So that we have seen how to bias your transistors in maximum omega t for maximum omega t when GM is fixed. In a nutshell, you'll have to basically reduce the CGS for the same GM, which means you'll have to have higher overdrive. Okay, so now, so what is the key takeaway till now? The key takeaway in today's lectures are the fact that we understood the other noise contributors are in a MOSFET other than, or thermal noise contributors in a MOSFET other than the channel noise, namely the noise due to Rg. We saw how to reduce the noise due to Rg by putting transistors in parallel. Then we also saw there is another high pass gate induced noise, right, which is supposed to be correlated with IN, but I made a statement that as it turns out, even if you do not take that correlation into account, there is not much harm done. But we did not take that, we kind of ignored the total effect of IGN going in the next in the example that we did. as it turns out, you can ignore it unless you are looking for extremely low noise amplifier. And for example, if I'm looking for a 1 dB noise figure or sub 2 dB noise figure amplifiers, then I cannot neglect that IGN. But if you are looking for 3 dB, sub 3 dB, slightly higher than 3 dB, then it is okay to neglect IGN. I mean, that is, again, uh, it's a very technology specific comment, but in most CMOS bulk CMOS processors, that is correct. The other example that we did was, let's say I have a common source amplifier which is probably biased with the inductor, so I don't have to bother about the noise from the inductor. I only concentrated on the short circuit noise current, and we derived the noise factor for this particular configuration, and we saw that whatever we do, we'll have to probably burn more current or and bias my transistor for higher and higher power drives, right? So these are the key design takeaways till now to make a low noise amplifier, right? So note that we have not yet put things together. We have not yet considered matching and noise simultaneously. So that is something we are going to do in the next lecture. Okay.